Welcome to The Explainer. You know, we trust them every single day, but we probably don't think twice about what's actually going on underneath our feet. Today, we're going to explore the hidden engineering of hydraulic elevators. And we're using a guide from the experts at Novan Puglia Elevator to see what it really takes to lift tons with, well, just fluid.
So what is this powerful, invisible force? Well, it's not magic, though it kind of feels like it sometimes. It's actually a fundamental law of physics that lets us multiply a tiny bit of effort into a massive amount of lifting power. It's the silent, reliable workhorse inside so many of the buildings we use every day.
And here it is, the big one, Pascal's law. This is the bedrock of all hydraulics. You probably remember the basic idea from school, right? If you've got a fluid in a sealed container and you push on it, that pressure spreads out equally, everywhere. But it's the way we use this law that is just pure genius.
Think about this. Have you ever squeezed a plastic water bottle so hard the cap shoots off? That's exactly it. That's Pascal's law in action. A small push with your hand creates enough pressure to launch something. Now just imagine scaling that idea way up. Hydraulic elevators use that very same principle to turn the pretty modest power of an electric motor into a force that can lift a car packed with people.
Okay, so that's the theory. But how is this principle actually put into practice? Let's break down the anatomy of the machine that makes it all happen. Let's look under the hood.
So you've really got four main players working together in perfect sync. It all kicks off with the power unit. You can think of that as the heart of the system. It's got a motor and a pump. That heart pumps the system's lifeblood, the hydraulic fluid, from a reservoir, sends it through a whole network of pipes, and pushes it into the hydraulic jack. And the jack? Well, that's the muscle. That's what does all the heavy lifting.
And what's really amazing is that for all this power, the operation is beautifully simple. The whole system basically does just two things. It goes up and it goes down. To go up, the pump forces oil into the cylinder, pushing the piston and the elevator car upwards. To come down, it's even simpler. A valve just opens up, lets the oil flow back into the reservoir, and good old gravity does all the work for a nice smooth descent. It's just a really elegant design.
But you know, just making it move is only the beginning. The real elegance is in the math, the super precise calculations that engineers have to do to make the whole system efficient, reliable, and, most important of all, safe.
And this is always the starting point. If you're an engineer designing one of these, this is the very first question you have to answer. Because literally every other calculation, from the pressure you'll need to the size of the motor, it all flows from knowing exactly how much weight you need to lift.
And, of course, you can't just design for an empty box. You have to design for the absolute maximum possible load. That means you're calculating the force needed to lift the car itself, plus its fully loaded capacity, all against the constant pull of gravity.
So here's the formula they use. It might look a little technical, but it's actually pretty straightforward. You add up the weight of the car and the maximum load to get the total mass. Then you multiply that by g, which is just the acceleration of gravity, and that converts the mass into the actual lifting force you need.
Okay, so now we know how much force we need. The next logical step is to figure out how much pressure we need in the system to create that force. And this is where you really start to see how everything is connected: the force, the pressure, and the physical size of all the parts.
See, this simple formula tells us that the pressure needed is just the lifting force divided by the area of the piston. And that reveals this really critical design trade-off. You can lift the same heavy load with less pressure if you just use a wider piston. But of course, a wider piston takes up more valuable space in the building. So engineers are always doing this balancing act between power and physical limitations.
All right, so we've got the power to lift the car. Great. But power is nothing without control, right? You don't want the elevator just shooting up to the top floor. So the next crucial variable to solve for is speed. How do you make sure you get a smooth, controlled ride?
Well, speed is all about flow rate, which we call Q. Just think of it like turning on a garden hose. The more water you push through the hose per second, the faster you fill a bucket. It's the same idea here. The more oil you pump into the cylinder, the faster the car rises. But wait, look who's back, the piston area. Remember that wider piston that needed less pressure? Well, now it needs a higher flow rate to move at the same speed. It's yet another engineering trade-off. So all of these calculations, the force, the pressure, the flow rate, they all lead us to the final piece of this puzzle. It's the question that puts it all together. Exactly how powerful does the electric motor that drives the pump need to be? The power you need is basically the pressure times the flow rate. But, and this is a big but, we don't live in a perfect textbook world.
In the real world, you always lose some energy to friction and heat. That's what this little Greek letter eta is for. It's the efficiency factor. Because no pump or motor is 100% efficient, you have to account for those losses to make sure the motor is strong enough to overcome them and still get the job done.
Getting the math right for movement is one thing, but the absolute #1 top priority is making sure the system is strong enough to handle incredible stress and has multiple fail-safes built in for when things go wrong.
Let's just take the piston. This one single long column is under enormous compressive force. I mean, it's holding up the entire weight of the car and everyone in it. So one of the biggest engineering challenges is preventing it from buckling or bending sideways under that load, because that would be absolutely catastrophic.
To solve this, engineers turn to something called Euler's formula. It's a classic, time-tested tool in structural engineering that calculates the absolute maximum load a column can take before it even thinks about buckling. This formula directly tells them how thick the piston walls need to be, and you can be sure they build in a very healthy safety margin.
Okay, so the piston is built like a tank. But what about the pipes carrying all that high-pressure fluid? I mean, what if a hose just burst? That's the nightmare scenario for any elevator, right? A sudden, complete loss of hydraulic pressure.
This is where a truly brilliant piece of safety engineering comes in, the rupture valve. It's installed right at the hydraulic jack, and its only job is to detect a sudden, massive surge in oil flow, exactly like what would happen with a burst pipe, and instantly slam shut. It's a dead stop. It locks the fluid in the cylinder and completely prevents a free fall. It's an absolutely vital fail-safe. So, as you can see, a modern hydraulic elevator is so much more than just a simple pump and a piston. It's a seriously complex system where a whole bunch of different engineering fields have to work together in perfect harmony.
And, you know, this summary from our source material at Novin Puya Elevator really just says it all. To guarantee safety, reliability, and performance, you need a deep, integrated mastery of not just hydraulics, but also fluid mechanics, solid mechanics, and electrical engineering. It's the whole package.
From the simple elegance of Pascal's law to the life-saving precision of a rupture valve, there is just a huge amount of unseen engineering that goes into creating that smooth, quiet ride we all take for granted. So the next time you step inside and press a button, maybe you'll think about all the invisible forces, both the physical ones and the intellectual ones, that are working together to lift you safely to your destination.